Welcome, everybody, to our Data Science in 30 Minutes. This is a series we hold here at the Data Incubator, where we get people who are practicing data scientists in to tell us a little bit about what they do. My name is Robert Scroll. I'm the technology lead here at the Data Incubator and one of the instructors out here in our San Francisco office. So for those of you who don't know about the Data Incubator, we do a number of data science training related activities. One of them is our Data Science Fellowship. This is a program for PhDs and master's students who are looking to get into the industry, get a job as data scientists. This program is completely free for those fellows who are accepted. Applications for our spring session, which will start in March 2019, just opened. Go to thedataincubator.com to sign up and start your application for the fellowship. In addition to this fellowship program, we run a number of online courses in the evenings. These are designed for working professionals who want to get a little more experience with things like Python or machine learning or TensorFlow. Again, you can find out all about those by visiting us at thedataincubator.com. We also do a number of training events, both at different companies, and we have gone to a number of different conferences. For more information on these things, including the courses that are offered, again, thedataincubator.com. But that's not why we're here today. Today, we're going to talk a little bit about data science in practice, and that's the goal of this thing. So we've had a number of people in the past, including Kirk Bourne, from Booz Allen Hamilton, Becky Tucker, data scientist at Netflix, and Jess Stroth from Quantopian. Today, very proud that we have Zoubin from Uber, as well as Cambridge University, to talk to us about some of the things he's doing. But before we get on to that, just to remind you that if you have questions, and I hope we get some questions coming in here, please put them in the YouTube chat area. We will sort of track those as those come in, and at the end, we'll have a little bit of time to pose those questions to Zoubin. You do need a Google account to make this work. So I think I've covered all of my bullet points. So we're on to Zoubin now. He's the chief data scientist at Uber, is that correct? And also a professor at Cambridge University. I hear that's a pretty good school over there. And he's going to talk about exploring the frontiers of machine learning.
Great. It's a pleasure to be here. I'm going to give a bit of a whirlwind tour of frontiers of machine learning and AI, and then I'll try to leave a few minutes at the end for questions. And as Robert said, I'm the chief scientist at Uber, where I lead the AI efforts there, and a professor at Cambridge. Okay, so I'm going to just share some slides now. And off we go. Okay. Great. So let's talk about frontiers of machine learning and AI. Now, I'm sure this community of data scientists knows what machine learning is. I'll give you my definition. I think of it as an interdisciplinary field focusing on both the mathematical foundations and the practical application of systems that learn from data. And it combines ideas from a lot of different fields: statistics, computer science, engineering, cognitive science, etc. Now, machine learning is best understood by contrasting it with traditional computer programming. In traditional computer programming, we give computers detailed instructions, a sort of fragile, step-by-step predictable recipe. Whereas in machine learning, we give computers lots of data, examples of inputs and outputs, and an algorithm that finds patterns in data. And this gives us a more statistical, less predictable, and sometimes more robust pattern matching type behavior. Now, there's a lot of terminology thrown around: AI, machine learning, data science. I see all these as being very closely related. I want to just spend a minute on this slide here. Let me see if you can see my pointer. Machine learning relates to other fields. This is a slide created by my colleague. Of the theoretical foundations of machine learning and related areas. And statistics is firmly in the theoretical foundations. Statistics is the mathematics of data, learning from data. But then other areas like deep learning, signal processing, and so on, the sort of methodologies kind of live here. And, you know, to oversimplify a bit, but I think it's still useful, in statistics, people generally look at simpler models with fewer parameters and some theoretical guarantees, whereas in machine learning, often people look at very complex models with many parameters, but much fewer guarantees. Now, these theoretical foundations are used for downstream applications, and whether you call yourself a data scientist or an AI researcher kind of depends often on what sorts of problems you're trying to solve. So are you trying to extract value and knowledge from data? Maybe we want to call that data science. Or are you trying to recreate intelligent behavior? Maybe we would call that AI or machine intelligence. Now, I'm not too fussy about these terms. I think this is all one big, beautiful mess. All of these fields and areas are related, and the techniques are all very closely related, and it's worth knowing about all of them. In machine learning, people generally think of a few canonical problems: classification, regression, clustering, reinforcement learning, where you have an agent making sequential decisions, interacting with the world. And these classical problems have their counterparts in statistics, control theory, decision theory, and other disciplines. Everybody probably knows it's an incredibly exciting time for machine learning. And it's exciting because of all of the downstream applications, the sort of substrate that it is for other things. Conversational AI is one such area. Machine learning is the underpinnings behind all of our speech recognition, machine translation, dialogue systems. Machine learning is also the substrate upon which all modern computer vision is done. Object face handwriting recognition, semantic segmentation, image captioning. For example, like in this example where just from the raw pixels, an algorithm basically can produce these phrases or sentences that are text captions of what's going on in the image. And this seems like magic until you realize that actually, if you throw tens or hundreds of millions of labeled examples of images with captions, there's enough statistical regularity in there to learn that function that goes from the pixels in an image to the words in a caption. Machine learning is also incredibly useful for scientific data analysis, areas like bioinformatics, medicine, astronomy. Machine learning underpins all recommender systems currently. Autonomous vehicles rely on machine learning algorithms for their sensing, perception, prediction, and to some extent decision making. This is an area that has been in people's imagination for decades. Here's a slide from 1989 of Alvin driving at 70 miles per hour on highways using a neural network. Things have evolved quite a lot since then, and now we see self-driving cars in our streets, and hopefully soon to be commercial services. Machine learning also helps with robotics. This is an image of a robot that can recover from damage. Machine learning has produced a whole bunch of breakthroughs in games. For example, famously, the Atari games being played at superhuman level, and then moving on to Go, poker, and other such games. And so these applications are, incredibly exciting. But what's the foundation? So I'm going to spend just a few minutes on the foundations, some sort of areas that I think are exciting, and then I'm going to end with a few minutes on how does this relate to machine learning and data science at Uber. So let's talk about the foundations. And one of the areas that people often think about in terms of AI and machine learning is human brain inspiration. AI inspired by the human brain. That's a very compelling story, but if you dig a little into it, you find that actually the human brain, you can do a back of the envelope calculation. I don't have enough time to go into it today, but it actually stores very little information about the world. The mutual information between the inside of the brain and the outside of the brain, the outside world, is maybe around 2 terabytes, give or take an order of magnitude. We also know that human reasoning is flawed. We're terrible decision makers. We're not good at estimating probabilities and risk. We have very little short-term memory to work with. Our perception is limited. It's evolved to see certain patterns, but not very good at other kinds of patterns. Human communication has very low bandwidth. Just think about me talking right now. There's very few bits of information being conveyed compared to a modem, for example. On many tasks, computers are way better than us. And in my view, actually, AI is already here. We just don't want to admit it. I think it's useful to think beyond human-centric AI and focus on the potential of AI, machine learning, and other data-intensive methods to solve problems humans are not good at, to complement human intelligence. And that's where I think the narrative should be focusing. Now, having said that, the most exciting recent area of machine learning has been deep learning or neural networks, which is very much inspired by neurons in the brain, very loosely so, but certainly inspired by brain-like computing architectures. Deep learning methods are essentially neural networks of the same kind that were around in the 60s and then again in the 80s. And neural nets are just tunable nonlinear functions with many parameters. So in this case, for example, it might be a function that maps from an image to labels for things that might be in the image. And it's a nonlinear function that goes from the pixels in the image to possible label categories. And the function is computing using a number of layers of neurons. And neurons are just simple computing elements. And it's called deep learning because these networks have many layers. Okay, so it's deep in the sense that the computation occurs in a number of stages. The weights connecting these neurons are tuned to reduce errors on some training data. So you throw huge amounts of data at these things and train them to perform well. Now, thought about this way, they're not really all that exciting, maybe, except that there have been a tremendous number of breakthroughs that have relied on using tens or hundreds of millions of examples and these sort of tunable nonlinear functions to learn to produce all sorts of interesting things like the examples that I gave before. So it is hugely exciting. There's been a tremendous amount of progress. There's nothing magical really in here. But there are also some important limitations of deep learning. They're very data hungry and compute intensive. So the success stories are often because we had huge amounts of data, not because anything particularly clever was done with these deep architectures. And there's a lot of computation that goes into these learning algorithms. Deep learning methods are very poor at representing uncertainty. So often the outputs are probabilities, but often we can't trust those probabilities. They're generally uninterpretable black boxes. They lack in transparency and they're difficult to trust, which limits their applications in certain areas where you do care about transparency. You want to be able to figure out what's going on for legal or other reasons. And they're easily fooled by adversarial examples. If you haven't seen it, here is an example of that. Here is a school bus. The deep learning architecture correctly classifies this image as school bus. You had a tiny amount of pixel noise, judiciously chosen, and the neural net or deep learning architecture confidently predicts or outputs that this is an ostrich. Sorry, here's an image of a dog. You add a tiny amount of judiciously chosen noise, and again, you get a confident output that this thing is an ostrich. And you can do that with any image and any category that you want, essentially. You can make anything look like an ostrich by adding a tiny bit of carefully chosen pixel perturbation. So that should be troubling because you really don't want our system to be so easily fooled. Now, I'm going to shift gears a little bit and talk about a different view of machine learning. And instead of thinking about machine learning as, just learning these functions from data, let's actually step back and think about the probabilistic foundations or the statistical foundations of what it means to learn from data. And here I'm going to take, for those of you who are familiar with this, I'm going to take a very Bayesian view. So this is Reverend Thomas Bayes from the 18th century, who famously had a posthumous paper where he talked about Bayes' rule as a basic rule of probability theory. So here is Bayes' rule. It's, again, I'm sure most people are familiar with this. It's a way of converting conditional probabilities in one direction to conditional probabilities in another direction. And what we find is that if we just change the symbols, this becomes a lot more interpretable. So what Bayes' rule really allows us to do is to make inferences about hypotheses given data. So before observing the data, our beliefs about the hypotheses are represented by a prior. Then we observe some data, and we evaluate for every hypothesis the probability of the data given the hypothesis. We renormalize over all the hypotheses we're willing to consider. And from that, we get learning. We get the posterior distribution of hypotheses given data. And when I talk about hypotheses and data, what I really mean is data is anything that's measured, and hypothesis is anything else. Everything else is uncertain. So the trick is figuring out the unknown things from the known things. And the prior is the knowledge before observing the data. The posterior is the knowledge after observing the data. Of course, if you get new data, the posterior is the prior at the next point in time. So these very simple concepts can be used to build the foundations of probabilistic machine learning. So learning is simply updating your parameters in light of data using Bayes' rule. Prediction is averaging or integrating over all possible parameter values weighted by the posterior probability of the parameters, the predictions for each parameter value. And model comparison is also just an application of Bayes' rule to models given data. So everything actually follows from the sum rule and the product rule of probability. It's very simple, very elegant, and it helps you think about lots and lots of problems in machine learning and statistics. So I really like this framework. Machine learning isn't just about tuning parameters of something to lots of data using gradients. That's just the algorithmic workings of optimization. I think of machine learning in this model-based way. Now, well, how does it work? Apologies for the slightly fuzzy figures here. If I'm trying to do classification, one simple method might give me a class boundary like this orange line here, confidently predicting that everything on this side is in the blue class and everything on this side is in the red class. That seems overconfident to me. That seems unwarranted given the data. Bayesian methods consider, in this case, the whole probability distribution of plausible decision boundaries, and then average over them, and you get slightly more sensible uncertainties coming out. Of course, part of the failure mode here, the overconfidence here, is the fact that you limited yourself to linear boundaries, and you should have considered nonlinear boundaries as well. So better calibrated uncertainties, I think, are hugely important for all sorts of problems in machine learning and AI. And it's really the foundations of learning from data. I'm just going to dive into a couple of interesting projects I've worked on over the years, some at Cambridge University and some at Uber. So this is a project called the Automatic Statistician that we started at Cambridge. And the idea there, we could call it the automatic data scientist, but maybe the audience here wouldn't enjoy that. The idea here is data are ubiquitous. There's great value from understanding the data, but there just simply aren't enough data scientists, statisticians, and machine learning experts. So why don't we develop a system that automates some aspects of model discovery from data? Now, think of it as giving data scientists some superpowers rather than replacing data scientists. And the basic idea here is we want to take data in the form of maybe tables of numbers or other kinds of data, and we want to go through a loop that searches for models, finds a good model that can make predictions, but also translates that into a report about the data. And I'll show you a demo of this. This is, you can look at it on automaticstatistician.com if you want. It ends up producing models that are actually quite competitive from a predictive point of view in certain settings. But let me just actually, let's see if I can run this demo. Get rid of this. Okay, I don't think, actually, I may not have included the video for the demo, sorry. So what the demo would show is you upload some data, and then the system produces a report, and it's quite fun to watch. It tells you what it thinks the variables are and writes a report saying these are the things that is covered in the data. And it's all written in a human readable form so that you don't have to be an expert in data science here. Okay, apologies for that. I should have tested this, but let me move on. I have a lot of material anyway. So the last bit, what I want to do is I really want to talk about AI and machine learning at Uber. So where does it all fit within the world of Uber? So AI and machine learning are absolutely central to Uber's mission. They're really at the heart of the company. I call this the algorithmic heart. And so this is an image of something you could think of as an algorithmic heart. But really think about it as the beating heart of Uber as an algorithmic company. These are the algorithms that allow us to optimize the world, that allow us to create those experiences for our riders, our driver partners, our eaters, the restaurants on our platform, all of those experiences that make delivering food and moving people around in the world more efficient. And it also allows us to just basically generate value for people that way. And machine learning and AI are really at the core of what Uber does. And broadly speaking, I'm talking about going from data through models to algorithms, predictions, and ultimately optimized decisions. And it lives everywhere at the company, where we're modeling ETAs, traffic events, dynamics of cities, predicting driver supply and rider demand, natural language, fraud detection, security applications, autonomous vehicles, of course, etc. Now, to solve all of these problems, we need a whole range of AI, machine learning, and data science tools. Deep learning, probabilistic programming, combinatorial optimization, all sorts of things are being used. And our community of AI, machine learning, and data science people at Uber is very diverse in terms of expertise and techniques. But we're not just a generic AI company. I mean, I think of Uber as a very special AI company, and that's because, in some ways, the problems we have are quite exciting. And let me explain to you what I mean by that. This is a quote from Dara. Uber is a giant machine intelligence problem, and it's a particularly challenging problem because we're trying to optimize and navigate the real world with all the uncertainty that that brings. So, many of our problems live in the spatiotemporal and physical world. We interact with a complex network with many human agents and complex economic incentives. We want to optimize the movement of people and things around in the world. So I'll just talk about a few examples of our work in, some of these areas: conversational AI, deep learning, and RL. You can find out a lot more by visiting the Uber Eng blog under AI, with the tag under AI. Just very briefly, we have conversational AI systems, making Uber interactions as natural as talking to a friend. We have a lot of work in deep learning, including fundamental research. For example, a new deep learning architecture called CoreDeconv solves a very fundamental problem with convolutional neural networks. This was a very big splash recently. We have fundamental work looking at what is the intrinsic complexity of certain problems and the intrinsic dimension of neural nets. And sometimes we find that problems are actually surprisingly easy. So even if you're using hundreds of thousands of parameters, maybe you really only needed 4 parameters to solve a problem. We also do quite a lot of work in open source. Horovod is a framework for distributed deep learning. Pyro is an open source deep probabilistic programming language. And let me explain that for a minute, and I'm nearly done. So just briefly, probabilistic programming is an area of machine learning and AI, which basically develops programming languages for expressing probabilistic models. And they basically express models as simulators that generate data. And then you can do inference on those models automatically using a universal inference engine. This is a hugely revolutionary idea. I mean, I think of it as akin to the use of compilers in computer science, where no longer people had to write machine-level code when they had compilers. So probabilistic programming makes modeling that much easier. And I have a review paper where I talk about these things from around 3 years ago. At Uber, we've released an open source project called Pyro, and this is a merger or marriage between deep learning and probabilistic programming. And it's hugely exciting because we have the best of both worlds. We can model anything that can be implemented in a deep learning architecture, but we can also develop full probabilistic models in this language. At Uber, we also do a tremendous amount of work on deep neuroevolution, evolutionary optimization algorithms that have proven to be actually surprisingly good at solving some reinforcement learning problems. And we had a very exciting breakthrough, which I'll end with, in reinforcement learning from a few weeks ago. Let me set this up. In 2015, a team from DeepMind had a breakthrough where they beat at superhuman levels, a whole bunch of Atari games, but there were a few that proved to be major challenges in their own words. So games demanding more temporally extended planning strategies constitute major challenges for existing algorithms. That the most challenging one was a game called Montezuma's Revenge, where actually the DeepMind method in the Nature paper got 0 points. It just couldn't do it at all. And so here we are. Great. I hope you enjoyed that. That was our recent breakthrough from the Uber AI team on the most challenging exploration problem in Atari. So I'll leave you with that. Oops. Let's go to the next slide. Thank you.
Thank you very much, Zoubin. And I'm a little bit worried that now not only are computers going to take our job, they're also going to take our free time and our our entertainment. We got a couple questions come in from people watching online. Reminder, if you're watching this live, you can pose questions in the chat channel and we'll see if we can get them. But let's go through some of the ones we've already had come in. One of them is a very general question. There's going to be, I'm sure, no one answer to this, but what sort of computing power do we need to run machine learning models? And of course, there's going to be a difference both between the training and the prediction side of that too.
Yeah, so there's a very long answer to this. So for the major breakthroughs that require huge amounts of data, there are commensurately huge amounts of compute power that are thrown at this. Often, like, you have maybe a data center with a few hundred GPUs or more. On the other hand, there is a lot of machine learning you can do on small devices. And in fact, one of the frontiers of machine learning is really to get, the most out of our portable devices. So I think machine learning on device is one of the most exciting areas. Most modern smartphones already support some basic elements of machine learning. And so, we're pushing the frontiers.
Mm-hmm. One of the most impressive things I saw was a live object detection at 30 or 60 frames a second on a smartphone. And I was impressed.
Yeah, it's pretty cool. And especially, the paradigm there is you might train offline on a very large amount of data. And then what you might want to do is compress the model down, not using a standard compression method, but a sort of like, how to a statistical compression method, and compress the model down to something that will run with the memory and energy limitations of a smartphone.
Yeah. The next question here asks, how do neural networks compare to fuzzy networks? But I think you have to explain to me first, at least, what a fuzzy network is.
Yeah. So fuzzy logic is sort of branch of mathematics that relates to AI and machine learning as well, that's been around for a few decades. The premise of fuzzy logic is that pure logic, which is based on basically zeros and ones or true and false and so on, is not very good at solving many problems. And the people that work in fuzzy logic also believe that probability theory, where you have uncertainty over statements that are either 0 or 1, is also not good enough. So a community of mathematicians developed this area called fuzzy logic. That has percolated into neural networks and so on. A very simple concept there might be, instead of saying something is either hot or cold, you might say, it's like very hot, hot, lukewarm, cold, frozen, whatever. And so that would be like a fuzzy scale. Honestly, fuzzy logic has its fans and its detractors. I'm not a fan myself. I actually think we can deal with probability theory, continuous numbers, discrete categorical variables, and so on. We don't need anything beyond logic and probability theory. But there are many people who like fuzzy logic as well.
And I'm sure we will see.
Yeah.
We had a couple questions all on the same idea, which is, what do you think is going to be the best way to sort of overcome the problem of black box models, of understanding and explaining what's happening inside of them?
Yeah, that's a great question. And there are a number of ways in which we can make progress there. So at one extreme, we can limit ourselves to simple interpretable models. So basically, there's a body of work that around, for example, decision trees, where, if you have a shallow decision tree, you can actually understand what it does. If you have a linear model with integer valued parameters, you can think of it as a scoring system that you could explain to, a judge or a client or an executive or something like that. So that's one extreme. Keep your models interpretable. The other extreme is, go with the complicated models, but then try to put on top of that a layer that, I don't mean a neural net layer, literally, but I mean an algorithmic layer that tries to explain what the complex model has done. And so, if you look at how recommender systems work, actually, most recommender systems are incredibly complicated right now, but they will often say things like, you bought this, we recommend you this movie because you like this other movie. That's a layer of explanation. It's not really the full story, but it's enough to, get people comfortable enough to actually buy the item. So for interpretability and black box and so on, we need to think about who is, what is the purpose? Who is the end user? Why are we doing this? Is it for legal reasons? Is it for ethical reasons? Is it to convince the customer, etc.? And the answers are different in different cases. But I would encourage much more work on this. This is an area that I've worked on myself, and I really encourage work in this area.
Interesting. We have a person ask, I'm a deep learning transplant in Bayesian land. What are some promising, interesting ways of combining the two? I think that's probably the probabilistic programming you're talking about. Is that correct?
Yeah, that's one way of combining them, and we're very excited about that. We use that framework both in-house at Uber, but we also have made it open source so the wider community can use it. But there is even a simpler way to think about this, which is deep learning is, I kind of divide the world into models and methods. Okay, deep learning is about a class of models. Okay, these are nonlinear models with many parameters. And then when you think about methods, usually people think about a maximum likelihood type optimization methods for deep learning models. But Bayesian methods can be used on deep learning models. So if we divide up the world into models and methods, then Bayesian deep learning is simply the use of Bayesian methods on deep learning models. And in fact, over the last 3 years at the NIPS or NeurIPS conference, which is the main AI conference that happens every year, I've been co-organizing a very large workshop called Bayesian Deep Learning. And there's a huge community around that. It's an interesting topic. There's a lot of work still to be done there, but it's a way of getting neural nets to be a little bit more honest about their uncertainty is one way to think about them.
Yes. One of the fun things we do in the data incubator for teaching is we demonstrate some of these things, and you can get them quite confident about parts of data they've never seen before. And
great.
So we've talked a bit about theory here. So maybe we'll just end up with one question about your work at Uber. The question comes in, what's the most prominent data science problem or hurdle that you're trying to deal with right now?
Right.
At least that you can talk about.
Yeah. There are many interesting problems my teams are working on. I would say, one of the most interesting things about the problems we have at Uber is that spatiotemporal nature of the kinds of statistical models we have to build. So if you think about rides, there is supply and demand, and we're trying to basically build models so that we can optimize the way cities work. So try to model and predict supply and demand with all sorts of other exogenous factors coming in using fairly sophisticated, complex nonlinear models. And so this isn't something that my team alone works on. We try to help. This is a major part of what the larger data science community at Uber thinks about. And we try to help with our little bit as well in those sorts of optimization problems.
Well, it sounds like you have your work cut out for you.
Yeah.
So I think we will go ahead and wrap up now. We promised to only take a half hour of your time, and we've already gone over. So thank you very much for taking the time and sharing this with us. We've had a couple of people ask, are your slides online for them to take a look at afterwards?
So I will, I'll try to make something available and pass it on.
Great, thank you very much.
All right.
So thank you again, Zoubin. I certainly learned some stuff here, and I hope the audience did as well. Just a reminder about the Data Incubator, the fellowship program. We've just opened our application for the spring. Our online courses are always open for the next round, and our training courses. All of these information can be found at thedataincubator.com. So thanks again. Thanks you all for joining us, and we'll see you at the next Data Science in 30 Minutes.